A rigid ball of mass m strikes a rigid wall at 60 degree and gets reflected without loss of speed. Mass m gets rigid wall 60 degree reflects, okay, without loss of speed, vv. The value of impulse imparted by the wall on the ball will be, okay. See, to do this question, what we need to understand is the primary formula, which is impulse is equal to change in momentum, which is final momentum minus initial momentum. Since it is given in the vector form, we need to find out final vector minus initial vector. So I'll just explain the workflow. We'll find out the initial vector pi, we'll find out the final vector pf, and then we'll calculate the change in momentum vector. And then what we'll do, we'll find out the magnitude of the change in momentum vector. Okay, so how are we going to do this? Initial momentum, exactly, final momentum, change in momentum, and then magnitude of momentum. Okay, so what I'll do is we'll divide this into three parts: part 1, part 2, and this would be part 3. Okay, so let me draw the diagram first, and then we'll go to the part 1. So what do I mean by part 1? When I say part 1, I mean we are discussing only about this shaded region here, this much portion of the event that we are going to see. So we are going to discuss only the region where the ball is actually. So this will be part 1, right? This will be part 1 where the ball is actually hitting the wall. Okay. Now when the ball is hitting the wall, it is hitting with a velocity v at an angle 60 degree, right? So the given diagram actually represents a ball with mass m hitting the wall with velocity v at an angle 60 degree. Now what are we actually supposed to find out? We are actually supposed to find out the momentum vector, but what are we given? We've been given the velocity here. So what we need to understand is direction of momentum vector is actually the same as the direction of the velocity vector, which means if this represents the direction of velocity vector, we can safely assume that this over here represents the direction of momentum vector, which in this case would be initial vector pi. Okay, so that's the primary concept here. So if you've got that idea clear, let us now go into the finding out the initial momentum vector. So we need initial momentum vector. So what is initial momentum vector? It is a quantity which has both magnitude as well as a specific direction. So what is the magnitude of pi here? Magnitude of pi, we know that it is equal to mass into velocity because it is readily given in the question. Now what do we need to do? We need to find out the direction of this vector. And how are we gonna do that? Let us have a look at that. So okay, so to find that, what I'll do is I'll draw a diagram here. So let us say this represents the initial momentum vector AB. Okay, so AB is initial momentum vector. So this is magnitude of AB, which is equal to magnitude of initial momentum vector, which is equal to mass into velocity. Now see, what I'm going to do is I'm going to resolve this vector into two components. One, the vertical component, okay, and the other one, so let me call this as AC, the vertical component. Other CB is the horizontal component. So AC is the vertical component and CB is the horizontal component. Now let us try to give our maximum attention here. So how can we write vector AB as? So vector AB can be represented as a component, right? A component which is, okay, let us write the component of AB along the x direction I cap plus component of AB along the y direction j cap. Okay, so this is what we have. Now, okay, I think the better way to write it can be written as AB, a component of AB in the x direction plus, okay, component of AB along the y direction. Now, why did I write it like that? I'll explain the reason behind that. See, if I were to choose a reference axis here, so say if this is our reference axis, okay, this is our reference axis. This is where the problem becomes really interesting and conceptual. So look at the direction of the head here. So the direction of AC vector head is C. C is pointing downwards, right? Vertically downwards. Vertically downwards means it is acting. It is acting like this. It doesn't mean that it acts like this. Vertically downwards simply means that the movement direction of movement motion is along the negative j direction or the negative y direction. Okay, so this is AC. So AC here is actually moving along. AC here is actually moving on the minus j cap, right? Similarly, what is CB? To find the direction of vector, we focus on the head. The head is B. B is an arrow. Arrow is pointing towards the right, horizontally towards the right. So this is where the vector CB is going. CB is actually moving towards the positive x direction. Therefore, it is along the positive I cap. So if I were to write vector AB, I would write like this. Vector AB is actually x component, which is CB, which is along the positive I cap, plus y component, which is the y component. Y component is AC. And where is AC along? AC is along the, so we have AC, and AC is along the minus j cap direction. I hope the concept is clear. Please go through the explanation once again. Go through it once again. Those who are watching online, please make sure that you pause the video, come back to this explanation more time. Things will become really clear to you. We have done that. And if things are clear to you, let us go to the next part, which is utilizing the given value here. What is given to us? See, it is given to us that this angle here is 60 degree, right? This angle here is 60 degree. So I can say here that this much angle is 60 degree. In which case, tell me what is sine 60 from the diagram. We can say that sine 60 from the diagram is equal to opposite by hypotenuse, which is, okay, let me explain that also. So if this is 60, opposite side is AC, hypotenuse is AB, right? In which case, what is AC? AC is nothing but AB sine 60, right? So AC can be written as AB sine 60. Similarly, tell me what is cos 60? So cos 60 from the figure is cos 60. This is 60. Cos 60 is adjacent by hypotenuse. Adjacent is CB, hypotenuse is AB. So we can write cos 60 as CB upon AB, and therefore CB can be written as AB cos 60. Now I'm going to erase out certain things to make the board look less cluttered. Okay, so this is CB is equal to AB cos 60, right? Now what I'll do is I'll bring these values. I'll bring these values over here. So I can write vector AB as, what is CB? CB from here is AB cos 60. AB cos 60 along positive I cap, plus what is AC? AC is AB sine 60, so that it would be AB sine 60 along minus j cap. Let me erase out these things as well. Okay, now let us see what is magnitude of vector AB. We've written here that magnitude of vector AB is nothing but mv. And what is vector AB? It is the initial momentum vector. So the initial momentum vector pi is equal to magnitude of vector AB, which is mv into cos 60 I cap plus AB is again mv into, right, mv into sine 60 along minus j cap. Okay, so yes, this is what we're going to keep for the reference, and we'll bring this again in part 3. Okay, now having said that, let us move to part 2 of the problem. Now if you paid much attention to the part 1, I think part 2 will become really easy to you. But even though it's easy, I don't want to skip any step here. We'll go through the steps in detail. Okay, so the idea remains the same. We're discussing only the second part here, which is when the ball is reflecting away from the wall. And what is the idea? The idea is the velocity vector is at 60 degree, and if the velocity vector is 60 degree, we can safely say that the momentum vector final here is also at 60 degree with an angle of, with a magnitude of mv inclined at an angle 60 degree, right? Now in this case, let us call this as okay, so we use ABC, right? So let us use DE and F here. Okay, so if I were to say that this is the Mm, okay, so if I were to say that this is the final vector here, which is vector DE here, I know that vector DE will have both magnitude and direction. The magnitude is MV, but we don't know the direction. To find out the direction, what will we have to do? We will have to resolve this into two components. So we have one component along the direction here. So let us call this as the final vector PF. So this is final vector PF, the vertical component, and then another vector moves like this. So we have final vector along the x component, right? So this is what we have. Now, how do you write the final vector? So we can write that final momentum vector PF is equal to the one along the x direction plus the one along the y direction. Okay. Can we write it directly now? No. Why? Because we need a reference axis. So this is the reference axis of our choice. This is the reference axis of the choice. We have this as plus x. This would be minus x. This would be plus y, and this would be minus y. Again, let us use the term here. So this is df. So how do we find out df? Direction of df? Direction of df would be the direction of where the arrow is heading. So df is a vector, f is the head, f represents the head of the arrow, and the arrow is head of the arrow is representing towards downwards. So we can say that if this is vector d, vector df is acting along what we call as the minus j cap. Now, what is vector? Where is, okay, wait. Now we need to find out where this angle is, right? Oh, I almost skipped that part. Sorry, my bad. So if we were to represent the angle here, see if this, wait. See if this angle is 60, we can say that this angle is over here is also 60. Why? Because of them being alternate interior angles. Okay, so the angle we are going to use here is this angle over here, 60 degree. Okay, right. Yeah, so now coming back to the explanation. So we have minus j, and fe is the vector here, second vector. So if this is f, then fe is going towards the negative x direction. So just simple, fe, head of fe is e is pointing towards the negative x, and therefore fe would be in the minus I direction. Okay, so if we were to write down the final vector pf is equal to, it will be pf x along the x direction, which is ef along the minus I cap plus py is actually df. So it is df along the minus j cap, right? Okay, now what we'll do again, what we do is we bring out sine 60. What is sine 60? Sine 60 is opposite by hypotenuse. Opposite is df, hypotenuse is de. So I can write this as df upon de. So what is df from here? Df from here is de times sine 60. Similarly, what is cos 60? Cos 60 would be, this is 60, cos 60 is adjacent, which is ef. So it becomes ef upon hypotenuse, which is df, and therefore ef is equal to, wait, is there a mistake here? Oh, sorry, it's not df, right? It's d. Okay, so we have this ef into de into cos 60. And now let me erase out these things. Okay, now what we'll do is we'll write down the final momentum vector pf is equal to, instead of ef I can write de cos 60 along the minus I cap, plus instead of df I can write de sine 60 along the minus j cap direction. Let me erase these two. Okay, now we have done the calculation, and now we have both the initial vector and the final vector. Now all what is left is to subtract them. So give me a minute, let me just try to bring these concepts together. Part 1, sorry, oh my bad. So we have part 1 here. and this is part 2. So ball is hitting the wall, reflecting the wall. From this we found out the initial momentum vector, and from here we have the final momentum vector. And what is now we need to find out? It is delta p vector, which is the final momentum vector minus the initial momentum vector. What is the final momentum vector? So which is, what is pf vector? Pf is, oh okay, right, so we need to find out pf also. So pf is actually, what is de? De is mv cos 60 along minus I cap plus what is de? De is mv, so it is mv sine 60 along minus j cap. I'll write it over here. So it is mv cos 60 along minus I cap plus mv sine 60 along minus j cap minus the initial vector. Minus initial vector is mv cos 60 along the I cap direction plus mv sine 60 along the minus j cap direction. Okay, right. Now if we have both of these, let us open the brackets. So it becomes mv cos minus mv cos 60 I cap minus mv sine 60 j cap, minus into plus is minus, so this becomes minus mv cos 60 I cap minus into plus is minus, minus into this minus is plus, so this becomes plus mv sine 60 into j cap. If you observe it well, minus mv sine 60 plus mv sine 60 is 0. So all what we are left is minus mv cos 60 I cap plus this vector over here is minus mv cos 60 I cap. So this becomes minus 2mv cos 60 into I cap. Now this is where the vector notation becomes really important. So all of this is actually delta p. And what is delta p? Delta p is change in momentum, which is the impulse vector. So we have that the impulse vector I is equal to minus 2mv into what is cos 60? Sine 30 is equal to cos 60, which is equal to 1 by 2 into I cap. And therefore the final momentum vector I cap is equal to, let me like this, will be equal to mv into negative I cap. And if you take magnitude on both sides, what you get? Magnitude of the impulse vector is equal to mv. Okay, option as option A, mv.